All right, guys. Hello, those of you that are still here, if anyone. So we spoke about last time Poisson random variables, and we just have to finish off a small thing about it and move to the next, hopefully very interesting topic. So Poisson random variables can be thought of as a good approximation to binomial distributions and distributions similar to the binomial in the event when the probability of success is low and possibly unknown, and the number of trials is very large, and such that the expected value of the binomial is significantly lower than that of the number of trials, right? So for example, if you have 1 million trials and the product of a million trials by probability of success is like 2, then the Poisson distribution will be a great distribution to estimate number of successes. Good. And we learned that the expected value of the Poisson distribution should be pretty much similar to the binomial distribution, right? Parameter lambda. That is intuitive because the distributions are supposed to be alike. Good. And we carried out that as a calculation. We also could intuitively figure that the variance of the binomial random variable is NP, the product of number of trials times probability of success times the probability of failure. Now, if probability of success is low, then 1 minus p is very similar to 1. And then variance will also be very similar to NP, which is the parameter lambda, if, of course, you remember this. Good. And then we established this within this proof. Good. And so this is just a simple calculation. Okay. Now let's talk quickly about the properties of some of Poisson random variables. If x is Poisson with parameter lambda 1 and y is Poisson with parameter lambda 2, then these variables are independent, then x plus y will be a Poisson random variable with parameter lambda equal to lambda 1 plus lambda 2. Let's see why that is the situation. We're assuming independence here of the Poisson random variable. So suppose that we observed x plus y equal to k. That means that we had k successes overall. Some of them were from x, some of them were from y. Now, how could those successes have happened, right? So we had to have j successes where j is either 0 to k in the random variable x. And the number of successes in the random variable y had to be k minus j to add up to k. Okay, so it's a summation of those probabilities, which I can write as product because it's an intersection, right? So what happened here is what? What happened is probability of today we follow Friday schedule, yeah? That's why so little of you came here. What do you know? But no matter, we still carry through, correct? Because we know no Thanksgiving. We do know Thanksgiving. Thanksgiving is, like I play to my calculus students, is that song that you play, you know, for mathematics. Du heilig Kunst, in wie viel grauen Stunden? You holy art, in how many gray hours, etc. So guys, my poor little darlings, you came here and you wish to go? Or do you wish, like what I did in the morning, to watch What, When, Where? A very good, interesting show. You know, Что, Где, Когда, if you know Russian. She was not admitted. No subtitles. I can show you one question that is very remarkable, right? Что, где, когда. Apparently, I was told that today is Friday schedule. I might kind of cover some part of it, and then if you want to see one question about what, when, where, I can show you a very, very cool question, right?
Wait, is it Friday scheduled today?
I don't know. Do you think I know what is Friday schedule? To me, we meet and do mathematics, whether it snows or rains, or the comet is coming to destroy planet Earth, or somebody is becoming a new president. Doesn't matter, right? We continue doing mathematics. Good. Any objections?
Well, you think a president election outcome will change?
I mean, it's stupid to ask what I think, because what do I know, really, right? For my thoughts to matter, I need to know a lot about something, right? And what I know about presidential outcomes in general is not a lot, right? Experts, as you know what they say: people of understanding make mistakes in things they know nothing about, and this thing is one of them. I did observe some interesting things, or at least some different points of view regarding what was happening. But with that, we can talk if you're interested after the lecture. I can tell you, what I observed and what I discussed with my brother and whatnot, and not that it makes any difference to anything that happened. All right, guys. So before I continue, would you mind we finish this Poisson thing? And if you want to see that question, I'll show you that what, when, where question, or we can slug through other things. We actually, which is a terrible thing, a semester is apparently coming to an end very rapidly, right? More rapidly than somehow I imagined. I somehow felt I have a month, but it feels like I have less than that. So are you there, guys? I see 2 people. What about the rest of you? All right, we'll finish this part. You have nothing against it? Do you feel very trapped here? You can tell me honestly, right? Nobody is gonna go nobody is gonna go AWOL, not me at least. Write in the comments if apparently today is Friday schedule. Thank you for mentioning. I have no idea, right? I thought it's Wednesday. So, anyone? Guys, you have your will, right? You are individuals and the exam grades, they're not ready. Exam grades, they're not graded. So there is the exams and they have to be graded over the Thanksgiving break among many other things that I have to do.
And what about other exams?
Yes, it's coming. So I need to write you another horribly difficult exam. Right? Horribly difficult exam that I need to prepare for you so that you don't forget about me. And so many things to do.
We'll have 2 more or 3?
Yeah. 2 more with the final, I suppose, right? So I need to hurry up and give you, we're finishing chapter 4. Exam 2 is involving chapter 4. All right. So what are we doing? I think you're silent. I don't know. I don't understand the silence. Maybe it's like a silent protest. That means that we continue with the math. You came here, right? You came, you saw, and you studied. Okay, let's go on then. So probability here that x equal to j. I will show you at least that and y equal to k minus j. By independence, I can I can expand, and I have probability x equal to j, probability y equals to k minus j. Yes. Good. Good. Okay. So then what happens is when I calculate those probabilities by Poisson, we have this product here, and the corresponding product for y is here. You all see that, right? All you do is you take the parameter lambda, raise it to the right power, and divide by that power factorial. So we have this. Now, when I combine the lambdas I have here, I can factor e to the minus lambda 1, lambda 2. I just group this and that together. And I have this summation, right? And in the summation, what do I have here? I have lambda 1 to the j, lambda 2 to the k minus j. And here I have, I can put here, you can see, in the summation, I divide by k factorial, and then I multiply in by k factorial. And that's just the k choose j coefficient. And that's just a binomial theorem that you see over here. This is e to the minus lambda, the summation. And that's the expansion for lambda 1 plus lambda 2 to the power of k. And voila, we have a Poisson random variable where the sum is with parameter that's equal to the sum. Good. Are you even here, guys? In spirit or what? I only hear from 2 people or 3 at most. So I have no idea if you have spiritual present here, or you think, my God, why was I such a dope and I came on a Friday schedule to study probability, right? And how can I politely leave without incurring the wrath of the instructor? Okay, so then next, I mean, I do expect you to speak to me, right? If x and y are Poisson random variables with parameters lambda 1 and lambda 2, x and y are independent, then the probability that x equal to k, given that x plus y is n, is equal to n choose k times the, you see, so if x and y are Poisson random variables with those parameters and they're independent, then the probability that x equal to k, given that x plus y is equal to n, is it has a binomial distribution. It means that which of the n possibilities, which of the n were contributing success on the behalf of x, and then the probability of success on the behalf of the probability of success was lambda 1 divided by lambda 1 plus lambda 2 to the k, multiplied by lambda 2 over lambda 1 plus lambda 2 to the n minus k. And how do you obtain it? Very simply, just think about it. Probability x equal to k, given that x plus 1 y equal to n, is the probability that x equal to k and x plus y is equal to n, divided by probability that x plus y is n. Now, the numerator can be rewritten as probability that x equal to k and y equal to n minus k. Yes, n minus k. Then they are independent. So probability that x equal to k, it's simply e to the minus lambda 1 to the k over k factorial, right? That's this probability. And the corresponding probability for y, same thing, but e to the minus lambda 2 and lambda 2 to the n minus k over n minus k factorial. This we verified if they're independent, then x plus y is a Poisson random variable where the parameter is the sum of the parameters of x and k, x and y, sorry, right? So that's what we have on the bottom. Now, when we simplify everything, we see that the k factorial and minus k factorial and n factorial form the n choose k part. And then we have lambda 1 to the k, lambda 2 to the n minus k. And I can break lambda 1 plus lambda 2 into power k and power n minus k, rearrange terms, and I have this, this value here. Here is an example, okay? Number of people entering post office on any given day is a Poisson random variable with parameter lambda. Show that if each person who enters the post office is a male with probability p and female with probability 1 minus p, then the number of males and females entering the office is an independent Poisson random variable. Okay, can you do that? And I will search for the question of what, when, where, so that you are not bored. You there? Can you hear me? Yeah. So with fast, right, I will show you. You see, you cannot leave this class without knowing this great game. Everybody that I know is interested. I was translating it today to my Germans and before to other people. All right. Are you ready? Let's solve this question together. Good. So what's happening here? Okay, so the number of people entering the post office on any given day is a Poisson random variable. Why? Because maybe it can be approximated somewhat by binomial. That's why you might think it's a Poisson. I hope it makes sense. You see, anything that is some sort of number of trials, lots of trials and success or failure, that might be Poisson random variable. You might imagine that, say, the total population of males in a particular city, what's the likelihood they will come on a particular day to this post office, right? It's very unlikely that each individual will come there, but some individual might come with some probability. There are many trials, and the chances of success are very low. So do you understand why it might be natural to assume it's a Poisson distribution? Yes? Alejandro, yes. Chabeli, yes. Abhishek, Mehrab, yes? You are here. Yes. Yes. Yeah. Okay. And so then let's say we want to know what is the probability that exactly K males enter this post office. You see, what's that probability? So the way I decided to calculate it is that the probability that exactly K males come in, it means that the total number is how many people enter. It's Z equal to N, right? So there are N people that enter. So and so that's the Poisson part, right? So then we know that probability that X equal to K, given that N people entered, it's a binomial distribution. You see, so what I do is I say X is equal to K, and Z is equal to from K to infinity, how many people came in, right? And that we can write as a summation. That's what you call that's conditioning here, yes? And so N equal to K to infinity, P equals to K, Z equal to N. That would be N choose K, P to the K, 1 minus P to the N minus K, lambda, and this probability that Z is equal to N is lambda to the minus e to the minus lambda to the N factorial. Now, what is that equal to? Okay, so first of all, I can break e to the minus lambda into e to the minus lambda P and e to the, what is it? Did I? 1 second. So yeah, so we can break the n factorial thing here into well, we can write n choose k as n factorial divided by k factorial n minus k factorial, and then I forgot, I think, to distribute here the e to the so you see what I did here. I have e to the power of minus lambda can be written as e to the power of minus lambda p plus lambda 1 minus p. Yes, so I can break it apart. You see, I can break this apart and write it as e to the minus lambda p, e minus lambda 1 minus p. That's the idea here, right? I think I forgot, so I'm going to clear it. I think I forgot to write here e to the minus lambda 1 minus p. I believe it's missing. Okay, So when I break it apart, and I can also break this lambda. I can look at this lambda and write it as lambda p. So lambda to the n is lambda p plus lambda. Yes, let me maybe do it on separate sheet here, right? So what we have is that probability that x equal to k is the summation where n equals to k to infinity of the probability that x equal to k and z, the total number of people, is equal to n, which is the summation n equal to k to infinity probability that x equal to k given z equal to n, probability z equal to n. So far, everybody understands what I've written, guys? Completely clear? If not, please don't make me waste my breath in vain. Let me know if something is not right or something isn't clear for you. You understand how I did it? I have a bunch of people entering the post office, and the distribution of people entering in this post office is some Poisson with parameter lambda. Because you can imagine there are, let's say, a lot of people in the city, and each particular person is like a trial, and the trial is success if that particular person enters the post office during the day. And if you have, let's say, New York City, it has 9 million people. Each particular person is unlikely to enter today that particular post office. Good. So it can be modeled as a Poisson distribution, a good approximation to how many people come to a given post office. And lambda is the average number of people coming into the post office. Is this clear? And is it clear what I've written this? Please confirm. Yeah. Good. And so what do we have now? Now I look at you see, each person coming into the post office is a male with probability p and not a male with probability 1 minus p. So we have k males, k men came into the office, given that the total is z. That would be the summation n equal to k to infinity and choose k. Which of the n individuals of those z equal to n individuals came, and p of those were successes, and 1 minus p were 1 minus p to the n minus k were failures. And then the probability that z equals to n is e to the minus lambda to the n divided by n factorial. That's what we have there. Yes? Good? Everybody sees this calculation so far? Then what do I do next? I have this n factorial, I have this n factorial. I can then cancel a few things. So then I can write it as the summation n equal to k to infinity. Here I cancel the n factorial, and I'm left with 1 over k factorial n minus k factorial. Then I see p to the k, and then I see 1 minus p to the n minus k. And then I see, I see this e to the minus lambda multiplied by p plus 1 minus p. I can do that. And then I see lambda to the power of n. And lambda to the power of n is lambda p plus 1 minus p, all of it to the power n. Good? You understand what I did? And there was an n factorial, that's why this is 1. It was divided by n factorial, but I canceled it with the n factorial in here. So then here is what I do next. So it's summation n equal to k to infinity. Then I take p to the k, And here I have e to the minus lambda p, right? So I have e to the minus lambda p, and then I look at this summation, and I see here lambda. It's all here. It's supposed to be all. I see this as let me just write it as maybe. Yeah, here I actually don't need this p here. I just need the lambda. So it would be lambda to the power of n. I will write it as lambda to the power of k. And then I have, and I place here k factorial. I take this k factorial, I borrow from here. And then I have multiplied by e to the minus lambda 1 minus p, which I carried from here, and multiplied by lambda to the n minus k, and then the entire thing is multiplied by p to the k 1 minus p n minus k, which if I regroup, look at it, I can factor out everything that has a k factorial. I have the pk, I have the lambda k, so I can factor out e to the minus lambda p. I can write it as lambda p to the power of k. That means I grouped p to the k and lambda to the k divided by k factorial. And then I have the summation n equal to k to infinity. And here we have, I forgot, by the way, to divide here by n minus k factorial. And here I have e to the minus lambda 1 minus p. Lambda 1 minus p to the power of n minus k divided by n minus k factorial. And this summation simply is Poisson distribution. It sums up to 1. It's all the possible values that add up to 1. So this summation is simply equal to 1. And I see the distribution for x. That's really the idea here. Okay. I hope you understand me. So that's what I get. So I simply end up with e to the minus lambda p to the k over k factorial. I hope you're hearing more than just lambda to the k, right? And similar calculation will follow if I have x and y independent. That will be true for y. The distribution for y will be that y is equal to j with probability e to the minus lambda 1 minus p, lambda times 1 minus p to the j over j factorial. Okay. All right. Let me show you this question to wake you up a little, right? Some people are jealous, actually, right? So let's see. Okay, ready? This game, this is I'll translate to you what it is, and it's a unique game that exists in Russia. It's an intellectual game show, and here is the idea: the people around the table are what you call knowers. They're good at solving riddles. They were specifically selected to enter a club. They are not just one time there. If you have, by the way, good questions, we can submit a riddle against them. So you as a viewer, you submit questions against them. The questions that are deemed to be good enough are placed on the show, and you win money if you are able to defeat them. They're supposed to answer the riddle in 1 minute. Okay? So let me give you an example of the type of riddles that they give. I can give you a few more if you are interested. Are you ready? I will give you more than 1 minute to think about it. Okay? So get ready, set, let's go. Those are the young generation. Yes, well, yes, Valeria. We'll see. It's a hard game. A knife and an onion. I'm not sure. I mean, I would have not thought of it because, well, what do I know about, right? So it's supposed to be easy objects, all right? Interested in one more, maybe about music or something else, or tired and want to rest? Let me know.
How are you supposed to know this, though?
Yes, some of them I have no idea how you're supposed to know. Some of them are very funny, really, right? Today I translated one that was very funny. But you see, it's of course the players are in Russia, so they do know. So they have certain common knowledge that maybe you do not know. But there are some others that other questions that are.
They debate.
What happens? Okay, so the idea of the show is this. Okay, so I'm not sure what happened. They win stuff, right? But they win. So the viewer, if you're as a viewer, if you send a question that they cannot answer, you win money. So you win for a question like 100,000 or 200 or even 600,000 rubles, which I don't know how it translates to dollars. Maybe it's not like $100,000. It's much less. But I don't remember by how much less. Maybe Valeria knows.
$5,000.
How much?
Like 1,000 or 2,000.
So if you win with a question and you get $1,000 or $2,000, right, or whatever else, and I don't exactly think. I think the knowers get also prizes of sorts, right? If they win it correctly, or maybe they just play for the pleasure of winning. I don't exactly know.
What do you get when you like are you get into the club?
Well, I do not know. You see, I mean, I only saw a few episodes. I don't know, but you see, now you want to start a club. I see, right? So you see, if you actually listen to the way those people speak, they are very intelligent, right? They're very quick-witted, intelligent, and they're not like your common person, right? So people in the club, anybody there that is speaking, they are very interesting people.
Well, it's like status. It's like you can tell in Russia that you belong in this club in some districts, and people will be like, "Oh, wow, you're smart."
Yes, it's exactly. It's like that. Okay, so you, Valeria, what city did you come from, by the way?
What city? Chelyabinsk.
Chelyabinsk. Okay, but not yes, not from those central Moscow places, right? Not Moscow, Petersburg. I see. No. All right, guys, do you want to hear one more, or what's up? Or you are tired of it, of this game? There are some really cool questions, of course, and that's just one episode. There are many episodes, right? Okay, I think some people already decided they spent enough time with poor old Arkady. All right. Well, so tell me if you want another question, let me know. If not, again, I wish you farewell. Auf Wiedersehen. See you soon. If you can come up with a good question, we can translate it. I will give you all the credit. If it's your question, I'll help you translate it. We can send it to them.
Divide the cash.
Huh?
Then we'll divide the cash.
No, I mean, I'll let you have the cash. I'm not greedy. Right? It's fine. I mean, I'll give you the pleasure of winning if you can win. Okay. See you next time then, I suppose. See you on Monday if you are leaving. All right. Or if you want another thing, let me know if you want another question. But don't be shy. Let me know what you want. You see?
Well, Professor, you promised to tell us what you think about election.
Well, I mean, when everybody who doesn't want to listen about it will leave, I can tell you what I think about it. Which is, by the way, not so curious because what can I think about it? I do not know anything really, right? It's too complicated for me personally to be able to do. I can show you. I can tell you what one thing that was observed that was rather interesting, perhaps. But then, how do you judge this particular one thing? Okay. All right. What when you remain, guys? I'm stopping the recording. Do you want to hear anything else? Are you interested in talking to me, or what? You want to see another?